My guest, Jim Holbury, PhD, is the founder and CEO of Grid Mobility. And Jim, when I was up there, when we met in Seattle, I asked you what you wrote your dissertation on, and I remember it scared the daylights out of me, but I don't remember what it was. Do you mind?
Sure. So my dissertation was well over a decade ago, and what I studied was the removal of polymers and plastics from recycled wood fiber or paper. So my focus was the recycling market, but I drilled down deep into actually separating a fiber that could be recycled from plastics that were actually contaminants. And the driver, as you may recall, Craig, was the Clinton administration overnight changing the whole paper industry by stating that the government will buy no paper that does not have a recycled content over, I think it was 75 or 80%. So
Post-consumer?
Exactly.
Right. Yeah, I do remember that. Well, very good. That sounds interesting, and certainly your current endeavor. Let's talk a little bit about grid mobility, and the title here, what color are your electrons? So the concept is obviously not that electrons have color, which they don't, at least literally, but metaphorically you could say we want people who have a concern about sustainability want to buy what we loosely call green electrons. In other words, electricity from renewable sources, solar, wind, geothermal, hydro, biomass, and so forth, as opposed to, for instance, coal, which I suppose you could call a black electron or a brown electron or something like that. Is that essentially correct?
Yes, that's correct. You're right. Electrons could not have color, otherwise, they'd be handing out probably a Nobel Prize for that. What we do is we distinguish the generation source and apply a color to that. So coal, perhaps we could say is black. Hydro, we could call that blue. But certainly renewables we call green.
Okay. So, and the concept here is that this is a platform that provides the user, whether that's a consumer or a business, probably more importantly a business because they consume more, and certainly more kind of on-peak stuff. So this is a platform that that provides that user the capability of selecting where times during the day to consume power that are more likely to be fed by renewable sources. Is that basically correct?
That's correct. That's correct.
Okay.
And we call it demand shifting. We call it shifting and shaping, where we enable businesses, IT infrastructure, etc., to shift those non-critical power operations to times when there's greater renewables delivered on the grid.
Okay. Well, very good. Let's cover some housekeeping thing before I leave this. Anybody who's having trouble listening to this broadcast on their speakers can simply call in that number at the top and enter the passcode from any telephone in the world, I suppose, and you'll be connected. Also, I guess I want to cover this, and that is that, well, that's your introduction on this. I wanted to also mention that I have, here it is. I just want to offer people the capability of entering questions. So just put them in the sidebar on your left, and we'll get to as many as we possibly can. Very, very good. So I guess we'll go in with this. Jim, you want to just take us through this, and I'll just move through these slides accordingly.
Sure. We're going to start at a pretty high level here to sort of paint the picture of energy in the United States, in North America, and then we'll drill down from there. So energy expenditures in North America in 2009 were roughly 8% of GDP. Out of that 8%, out of that delivered energy in the United States, approximately 1% or slightly less was generated by wind energy, and solar was considerably less than that. Those numbers are expected to increase, but this is painting you the broad picture. Go to the next slide. Maybe we can show some energy efficiency information.
Right.
So what I want to paint with this slide is look at the overall picture globally. Keeping in mind now that the United States is a highly a productive country. We're actually, as you can see from this slide, in the G7 on the top, at least from this data, which was put out 2005 analysis. So granted, it's a little bit dated, but we're a highly productive country, but very energy inefficient. So looking at efficiency of deployment of energy, we at least in 2005 were deployed energy more efficiently than Canada. Canada has actually in the last 5 years made strides to increase their efficiency, but we lag companies like Germany, France, UK, Italy, etc. Now, granted, we're at least 3 or 4 times as large in terms of population as Germany, and many times larger than companies like Switzerland. But the reality is that the deployment of energy, at least in 2005, shows that we were very inefficient. And that remains to be true with renewable energy, which we're going to talk about as we move through this presentation.
Yes, do me a favor though. Let me just go back. There are a couple people who apparently can't hear this presentation, and for them, I would simply ask to just use a telephone and call in that number 218-844-0842 and the passcode 524329. All righty. So we want to go on to this one, I believe.
Right. I guess you can hear me okay, right? Is that right, Craig?
No, I can hear you fine. And there are people who, every time we do one of these, there are people who can't hear it correctly. So that's why I provide. But you can listen to it on your speakers or through a phone line. I recommend you don't do both because you'll have a mess on your hands. But
So again, I'm painting a broad picture here, showing you U.S. electricity generation types. So this is EIA information, very recent actually, that projects, takes 2009 data and projects out to 2035 to show what the generation by fuel type will look like in 2035. Now, you see a slight increase in coal, at least on a relative sense. A fairly significant increase in natural gas. I mean, we're looking at natural gas right now, particularly since we're at $4.19 a therm as of Monday, as a source of the future. Now there's issues with that we'll talk about later, but these projections show that gas is going to grow fairly significantly over the next 20-25 years. Nuclear is staying somewhere in the same scale, but renewables growing significantly. I would argue that this bar chart's perhaps even a little low, because the general consensus is that wind and solar will grow 5x in the next 15 to 20 years in the U.S. So I would say, depends on which data you're looking at, but certainly it's true that renewables are going to grow. We can go to the next slide and talk about capacity additions.
Right. Let me just chime in for a second and say, apropos of nothing, I don't believe projections that go out, 2 years, let alone 20 years. But having said that, the concept that we're still going to be burning a lot of coal in 25 years is kind of astounding to me. But whatever.
Well, I think you have to look at the source, and the EIA, is a very, the figures they turn out are typically very conservative. Now, this is also EIA data, and this is capacity additions. So this is looking at what is going to be, truly the capacity increases in terms of scale over the next same time period up to 2035. And as you can see, the bet is on natural gas. And a lot of that is price-driven. Natural gas is inexpensive now, but we don't have to go back very far to remember when when the price of a therm, which is a unit of measure, which is today, as I mentioned earlier, about $4.20. Back in 2005, that figure was more like $12. So right now we're banking on shale-driven gas delivered from the United States. If we have an interruption in that for whatever reason, I don't want to get into the controversy over fracking, but if there was perhaps an interruption in service, what you would see is these capacity bars for gas decrease significantly because capital would essentially be removed from that space as the price of gas would increase because of such an interruption.
Right.
And then to your point from the last slide, all of these bars would change, Craig.
Right, exactly. And when you refer to fracking, you're talking about like a public outcry about environmental or health dangers.
Right. I don't want to get into that controversy, but what I am saying is if the science proved to that the market was different than the conditions are now. We can talk about water contamination, etc. Then clearly capital would fly out of that space into another energy.
Yes, in a big way.
And I think what I want to point out here, if you go back, please.
Sure.
There's one is the bottom slide there. And that is combined, and this is a key point here, is that there's two type of major natural gas electricity generation plants in the United States. There's the combined cycle, which utilizes the thermal energy as well as the gas driven electricity generation directly, and they can the efficiencies can be quite impressive, up to 60%. General Electric has a plant out the reporting efficiencies of 62%. But the key here is it's single cycle plants, which are the plants that can be turned on and off within 45 seconds, maybe a minute, maybe 2 minutes, which are those that balance intermittency on the grid. Their efficiency is significantly less. Mm-hmm. So to put that in terms of CO2 generation, a combined cycle plant will generate somewhere in the neighborhood of 1,350, 1,360 pounds per megawatt. The single cycle plant, on the other hand, is more like 2,000, 2,100, something in that range for pounds of CO2 per megawatt. So there's a significant difference. So not all gas plants are equal.
Right. So and peaker plants tend to be single cycle, i.e. dirty.
That is correct.
Okay. Now, someone asked, there are a couple of good questions here, and one thing that does strike me about this, as it did Thomas Dinkel, who asks, it looks like there's a reduction in additional capacity and renewables over these years, which strikes me as strange on a good day.
That's right. Yeah, and so that's very good. So the EIA looks at this and states that in the next 15 years, to meet renewable portfolio standards, you're going to see an increase in both solar, biomass, and wind to meet those RPS goals. The reason that you see the decline after 2025 is because all of the legislation for renewable portfolio standards in the 29 states that have legislation and the other 7 or 8 that have energy goals, they all end in 2025. Okay, mm-hmm. So everybody's got to meet their goals by 2025. So the EIA says, well, look, we're going to have a big build-out, but after 2025, there's no more standards on the books, no more legislation that's going to drive that renewable portfolio to increase. So therefore,
right, and that I suppose gets at this.
Yes, it does. That's exactly right. So this is a snapshot, a fairly recent snapshot from the Pew Center on Global Climate Change. I give credit to those folks for generating this. I didn't. But you can go online and obtain a granularity on the goals within each state. But here you see in blue those states which have legislation on the books. let's just call it lavender, the Alternative Energy Portfolio Standards, which are not, the distinction here is that the utilities will not be levied a fee or, shall we say, a tax by the state that they're in if they don't meet that standard, whereas the blues will be levied a taxation by the state if they don't meet the RPS standard. And then you've got goals out there, which are non-binding goals. Now that's interesting because you look at a state like Florida, which has quite a large wind fleet. They don't have a binding standard in place, but they have goals. So there's it's all over the map. What we can say here is that the Louisiana to South Carolina, the southern states, all the way up to Indiana, have neglected or have chosen not to put in any sort of legislation. It doesn't look like that's going to happen anytime soon.
Right. Nor does a federal RPS look at all likely.
Unfortunately, not in this political climate.
Right. Don't get me started. Go ahead.
So I got one more slide here that is non-hydro renewable electricity generation by source. And what I want to show here, and it really goes back to the individual that posed the question earlier, stating that things seem to increase but not dramatically after 2025, and this is reflected here. What you see is a significant increase over the next 9 to 10 years in wind, as well as solar. Biomass increasing after that point rather significantly. Interestingly, what you'll see here is that geothermal, which can be used as base load, right? So continuous power, which is very desirable from the utility space because that will essentially those units will be substituted for coal, nuclear. All right. It doesn't grow all that dramatically, and we have some challenges with geothermal. There's great assets in California, been developed, but it's not an inexpensive source. So it requires great capital investment to develop.
And it's horribly risky. You can have you never know what you're going to get. There's no equivalent to the kind of intelligence that you have if you're doing oil and gas exploration. It's a very risky proposition.
That's right. So moving forward in these slides, we're going to focus on wind and solar because those are two intermittent sources, which have their own challenges.
And let me just say before we leave this, again, I mean, not to sound like I'm, telling the EIA that this is poppycock or whatever, but I mean, certainly, let's just take solar thermal, concentrating solar power as an example. So we could have a breakthrough. Here's a technology that's lagging, 25, 30 years behind wind and PV, that anything could happen in the next 25 years. I personally believe that this is going to be a huge source, which is kind of, I guess you could say it's semi-intermittent because it lends itself to storage solutions. You, of course, storage is cool, and maybe we can get low-cost storage. But the thing, I mean, not to kind of jump ahead on this thing, but what we're really about here with grid mobility is saying, okay, if you can store it, that's fine. Right now it's expensive. You've got all kinds of, compressed air, energy storage, and various other approaches on this thing. But there are only 2 implementations of compressed air on the planet. And there's a reason for that. It's a very difficult proposition. So this says, okay, if you can store it, fine. If you can't, here's a way of bringing the peak to the source as opposed to bringing the source to the peak. And that's what we'll be getting at here. But here's another slide that you wanted to talk about the horrible intermittency issues. Is that correct?
Well, these are challenges. Horrible might be strong, but these are challenges. These are operational challenges. This is data that's from the BPA. Granted, it's from 2009, but you could take a snapshot of virtually any week in most parts of the country. Not all, but you'll find that wind will curtail significantly. The weather changes.
Well, in this case, it went to zero for two full days.
But in this case, this is rather extreme. It went from 2,000 megawatts roughly on the 14th, 15th of May down to zero for about 2 days. So therefore, it's very difficult to integrate such 2,000 megawatts, this scale of units, onto the grid when you're trying to forecast the delivery in the case of the BPA for somewhere in the neighborhood of 17, 18 million people. And furthermore, we're going to talk about this in a couple slides, and I'm going to get ahead of yourself. But you would think you could get accuracy with predictions from forecast entities, companies that self-forecasting for a business, but that's difficult too. So this is the framing the problem here. Solar have similar challenges. On the left of this webinar, you will see a single unit in the state of Illinois. Solar production. The black curve is theoretical. If you will, the up and down blue line is actual delivered power. So these are clouds moving overhead, etc. And this is a very recent publication from Lawrence Berkeley National Lab last fall, 2010, where they took that single installation, and then they combined and looked at 23 installations that were networked. So these are 23 separate solar installations networked, and that's what you see on the right. Is the black line is if you will, the average delivered power from those installations. So you get closer to theoretical. All right, so that's the message here. You get closer to theoretical, but you still have intermittency, and so these are things we try to solve in real time as operationally as a utility delivering power.
Yes, and I would say that one on the left must have been a day from hell, right? I mean, that's...
Yeah, clearly I would argue that the authors here cherry-picked the worst day for this data.
Yeah. Lots of clouds, come and go.
Yeah, right, exactly.
All right.
And this finally, I want to give you a little bit of data on forecasting. Now, this is persistence base points from, it's actually BPA's data from an unknown forecast entity. But the message here is that even the best forecasts can't get below 5%, and even if so you see the red line, which is a persistence, a 30-minute persistence, which means we're looking out 30 minutes, and even that we're still 5%. But more importantly, most of the time we're out at the 20 to 30% error bar persistence, which means if you look at an error bar, if you look at something that's delivered by a commercial entity, they'll give you an error bar, an average and an error bar, and typically their error bars are no less than 50%, 25 each way from a midpoint. So now if you're a PJM in the Mid-Atlantic, if you're ERCOT in Texas, if you're a New England ISO, Cal ISO, where you're trying to bring wind fleets, solar fleets onto your grid, you're looking at these forecasts and you're saying, well, what am I really going to be delivered if in 30 minutes I'm only going to get maybe plus or minus 5-10%? How do I forecast tomorrow?
Mm-hmm.
Right?
Okay.
So this slide is, I'm going to move now into demand response, which I'm sure everyone on this call has heard of. Typical demand response that is out there now is it shaves during peak, and this is a service provided by and large by third parties that take information from utilities, have clients signed up under contract that can shave peak on the order of within certainly within the hour. So they're looking at curtailing megawatts when there's an event or a squeeze in supply. What I want to do with the next slide, if you will. Can you hear me?
Yeah, I put up the next slide. Can you do that?
I don't have it on my... So you've got demand response 2.0?
Yes.
I don't see it on the screen. But, okay, on this the webinar I have. There it goes. Okay. So demand response 2.0, which is what we're working on here at Grid Mobility, and there's other firms out there that are working on this as well, is the notion that we can shape demand based on the delivery of renewable. Okay, so what you see in this slide is and I'll explain this. The red line is what's called the load above baseline, which is really the non-coal, non-nuclear units. So those are typically gas units. The total delivered power here, this is PJM's data, would be somewhere on the order of 100, 120 megawatts of power delivered on a normal summer day. This load above baseline is on the order of somewhere between 20 and 30 as it fluctuates, and those are typically gas units. Now the green is overlaid, which is wind delivered. This is a simulation that Grid Mobility conducted, which shows that there will be times, even within a week in August, multiple times, where the wind capacity, typically at night, will exceed that of the load above baseline, so the ability to take that power onto the grid. So demand response 2.0 is simply the notion that we can shift demand either forward or backward in non-critical electricity consuming operations to absorb more renewable energy.
Right. Okay, and this next slide gets at that as well.
Right. So exactly. So what I've done here is I'm trying to show in some granularity how this works. So what we're doing, the blue line is the delivered wind, and the red line again is demand. It's the load above baseline, and typically that's the dispatchable portion of power delivery. So what we're saying here is that we want to shift consumption out of peak. Okay, and peak is typically, depends on where you are, but morning and afternoon peaks are not uncommon in metropolitan areas such as where you are, Craig, in Los Angeles, New York, but certainly there's other parts of the country that have midday peaks. But we're saying here, let's shift out of peak in those non-critical operations into the times when renewables are generated. We happen to, and there's a little bit of self-promotion here, I say that up front. We happen to have a software as a service technology that we're piloting in several states now that shapes power to renewable generated electricity availability. So we save money for our clients by shifting out of peak, those peak pricing periods, and moving into times of low price, but also when there's more renewables delivered.
Right. And at a certain point, I mean, I know that you're sensitive about talking about too much detail about how this works. But I mean, if there weren't a way of actually doing it, if this were all theory or this were all a wish, this would be a pretty dumb conversation. So the truth is that you do have a product, software as a service, that is effective in doing this, I guess is pretty much what you want to say. And we do have I guess we have this slide coming up that gets at this to some degree.
Yes, and I won't spend too much time on this because I want to give the broad picture here. But what we're trying to do is we're trying to connect businesses and IT infrastructure, electric vehicle fleets when we get to scale, and right now residences. We have a couple of pilots going on in the residential space to do just what we showed in the last slide: save money and lower their carbon footprint, but also give them choice in electricity, give them the ability for the first time to really choose their generation source, and connect that to the right side of the screen, which are the utilities and grid, and provide balancing and integration efficiencies, and keep it capital efficient. Because what we're doing is, and this is not rocket science, but what we're trying to do is connect existing assets and utilize the capacitance of those assets. So think about a building, maybe the office you're sitting in. It has its own capacitance, and deploy those in a capital efficient manner in advance of our country having the capital to support storage at scale. Storage at scale is very costly. Craig mentioned compressed air, flywheels. We can talk about this for for hours on itself. But suffice it to say that these are multi-billion-dollar propositions to put storage in at scale, and it's going to be a few years before we get there. So what we're trying to do is use today's infrastructure to achieve a level of efficiency gains and cost savings.
Right. And I guess the example that you gave when we first talked about this thing, in other words, if I say, okay, well, I'm a big company, I've got employees that start to work at 8 and they leave at 5, and I can't really do much about that. And they're going to be using computers, they're going to be doing whatever they're doing that's consuming power. Not much I can do about that. And I said, so give me an example of something that I could do if I knew that I had an option open to me. And you said, okay, well, imagine there's a campus that uses air conditioning by chilling water. Now they can chill that. They can move the time at which they chill that water by a couple of hours. It doesn't mean anything. What it would do is it'll save them money, and it'll be consuming that electricity with a much higher concentration of renewables. So that meant something. I thought that was a really good example.
Well, there's a lot of examples like that, and I won't go into it too deep. But you can imagine pumping water. You can imagine heating and cooling water, airspace. You can imagine a pilot that we have in the manufacturing space where they've got several 1,000-kilowatt furnaces, agricultural refrigeration. We have a pilot in that space just teeing up. So you've got a lot of assets out there that can consume energy, and it won't hurt them to shift because of either the manufacturing process has flexibility or insulation, such as in agricultural cooling areas, where a 1 hour or 2 hour shift is not going to interrupt the product or service they're providing to their customers. But at the same time, as you said, you can save money and reduce your carbon footprint. So I want to give you a case study that we conducted in 2009 for PJM Interconnection, which is the RTO that covers 13 states in Washington, D.C., about 50 million, a little over 51 million people served. And they asked us to model their wind from 2009 and inflate that to 2016, 2020 delivered wind, which they anticipate being somewhere in the neighborhood of 10% to meet those states' renewable portfolio standards, and determine the benefit of a 5% renewable demand response shift, focusing on those assets that we just spoke about briefly, Craig, which would be HVAC, boilers, etc. Mm-hmm. And then show the simulation. So I'm going to show you in the next couple of slides just how this would work.
Yes, let's just jump to a couple of questions from the audience, though. Here are two that are somewhat related. Are there rate structures in place that allow the benefits to accrue to the users? And this really gets into some... Why don't we just stay with this one for a second? Because it seems to me that, yes, there are a whole bunch of people who want to do the right thing at either the private, at the kind of consumer level or the corporate level. However, I would argue that there's a much larger segment of the population who wants to save money, and of course time-of-use metering provides that capability. But why don't we are there rate structures in place that do this now? In other words, that provide that financial incentive as well?
Great question. So there are time-of-use rate structures out there. So when we shift out of peak, there's compensation that will be delivered today. Similarly, at the utility scale, because increasingly with renewables coming onto the grid, this cost of integration is being passed on to the utilities. Good example of that is here in the Northwest. The utilities that use intermittent renewable energy are now, as of November, I should say, 2011, will be required to pay to have that power balanced. Okay. Now, so the second financial opportunity, to your point, is there is no current rate structure which will compensate the utility or the company for shifting into renewables. Moving forward, this is key, moving forward, because of the scale of intermittent renewables coming onto the grid, it's projected to, I think 5x in the next 15, 20 years. Certainly here in the Northwest, there's already two entities that have, and a pilot going on for a regional balancing market. Mm-hmm. So we see this happening coming down the pike here in the Northwest. Certainly, you can go back to PJM and have that dialogue with PJM, which we have. That's on the table in that market. And certainly, as we move forward, this is going to become, we believe, this is going to become a reality. So the moral here is save money today by shifting out of peak. You can reduce your carbon footprint. And I haven't talked about this, but there's green dollar savings there for companies that are trying from sustainability standpoint. And moving forward, we see this the future being a regional balancing markets developing where there will be a market to bid into.
Right. And this is the related question we had, and that is, when will brown electrons have an additional cost or tax associated with them? So in other words, is there and of course this is speculation on anybody's part, I suppose, but given the political environment, are we anywhere near what we refer to as internalizing the externalities? In other words, forcing the consumers and producers of electricity to pay the complete comprehensive cost for them right now?
Well, I'll turn around and get my crystal ball, or I'll pick up the other line and call Obama and see if I can get some information for you on that one. Sorry to be sarcastic, but this study for PJM, the date, you can see it was done in the fall of 2009, and as you may recall, madam or sir, who asked the question, the legislation on the Senate floor at that time was slated to put a price on fossil-generated, or shall we say CO2 generation for utilities. And the price at the time that was being kicked around was $25 a ton. And as we all know, that brown or black electron piece of legislation, depending on how you look at this, didn't make it through. And it would be pure speculation on my point to look out into the future and say that this is going to come to fruition in the near term. I have no idea. Of course, I have my own opinion of what I want, but
yes.
that doesn't seem to matter.
That's exactly. Nobody's asking me for mine either, Jim. Don't feel bad.
So as I'm going to show you a week's worth of data. You've already seen this slide. This is so this has been reviewed by PJM, just so we're clear. This is scaled wind delivered data from 2009 that's been scaled to reflect 10% delivered wind in 2015 to 2020 timeframe. Okay, so what you see here in this scaling, and it's in the box, is that the wind generated exceeds the capacity to take that wind onto the grid, i.e. the load above baseline, a little over 17% of the time. What's that mean? 17% of the wind's going to be wasted of that 10% total delivered.
And this is a disaster for all concerned. The way I understand this, anyway, not only is it obviously, if you're a wind developer, you don't want this. But from a utility perspective, they're going to pay a huge fine if they don't make their RPS goals in a certain state. Is that correct?
That's absolutely correct. Of the 29 that have legislation, all of those have some tariff that will be levied on the previous year if they do not meet that goal.
Right.
So the next slide shows the wasted wind. So what is that? That's about the wind percent of total is delivered is only about 7.9%. So we lose about 21.6% of the total energy that would have been delivered. And that's like saying, okay, here's an aluminum can in your hand. We've gone to great lengths to design that aluminum can to be recyclable, but there's no recycling bin, so I throw it in the trash. Mm-hmm. Well, that's the analogy I use for wind. I mean, we spend billions of dollars in putting in the wind fleet, and what do we do with it? Well, unfortunately, we're subject to Mother Nature, and it doesn't always arrive when our demand curve is at its peak, and we have to throw it away.
And that's called shed wind, you call it, right?
Yeah, the next slide will I think if we're in unison here, we'll show it. So what can we do with that excess energy? Well, we could sell it, and we do that here where I'm from, up here in the Northwest. We sell it to California, but there are transmission constraints, and those are several $1 million a mile to install. You can just look at Texas as an example. They're spending billions of dollars to take wind from West Texas into the Dallas-Fort Worth area, and there's a potential for negative pricing, which happens on a frequent basis, actually, both in Texas and New England. But RPS standards will change the pricing structure in the future, so selling it will become less attractive. Taking here where I live as an example, selling it to California will become less attractive in about 4 months when these utilities must meet RPS standards. So we could shed it. That's we've talked about that. We'd rather not do that, obviously. Or we can use it or store it. Now we'd like you to use it now. And renewable demand response, which is what we've developed, enables you to do that. There's a potential for replacing REC credits. In other words, providing the ability to quantify and validate your use of renewable energy. Or we could store it. But as I mentioned earlier, storage is a pretty high capital investment involved there. So I want to go to the next slide, if you don't mind, and show you what we can do when we use it. You didn't put in the simulation results, huh?
Well, I thought you didn't want that one.
Oh, I'm sorry. I wanted to put it on the webinar, just not up on the website. Well,
I can do that. Here you go.
Let me just close by saying that the simulation showed.
Well, I can do that. Here you go.
Oh, can you do that? That'd be great. Thank you. Are they there?
Well, I'm having a little trouble.
Okay. My apologies for those on the line.
I don't know why that's not displaying. I can see it in my little viewer here. You want to just kind of walk through the highlights?
I'll walk through that. So suffice it to say, ladies and gentlemen, that the upshot of that simulation, which took about 3 months to conduct, showed that with a shift of 5% of those that were consuming energy during those periods in PJM would integrate an additional 94,000 megawatt hours of electricity, and what we showed was that lost wind percent, which went from 21.6% in the shed wind, was dropped down to 15.5%. So we went from 330,000 megawatt hours lost down to 238. So we didn't solve the whole problem, but the point here was that this is an operational strategy that could aid in solving the problem. And furthermore, if you recall the CO2 savings, at the time it was $25 a ton, as I mentioned. That's integrating wind at the expense of natural gas, which would save about $1.6 million a week. So that information was received favorably at PJM. It, in fact, landed us not by our own initiative, but the power generating community is small, and suddenly we found ourselves in front of, quite literally, in front of, invited and then in front of FERC Chairman John Wellinghoff and his staff in D.C., invited back, and so we took that invitation, and to give him also a 1-hour tutorial on what we had conducted, which has led to us now starting a business and having a pilot here in the Northwest with BPA and then several pilots in the commercial space. So I'm sorry that you don't see that data, but as I said, this was at the expense of natural gas units. So now we can go back to your slide deck that you're running, Craig. Go back one. There was a slide you had up, U.S. industrial gas pricing. Right. So at the expense of gas units. So gas right now is pretty reasonable. It's a very attractive electricity generation source. But we don't have to go back too far in our memory to remember when the price per therm was quite high. 2005 even spiked in '09, dollars per thousand cubic feet. That went basically fourfold from what it is today, or threefold from what it is today. So the reason this is attractive to FERC, for example, is because bringing on more renewables, which is going to happen, we showed data suggesting that it's going to be quite high in the not too distant future, means there's going to be more gas plants needed to balance. It's just the way we balance renewables in 90% of the country. We do that with hydro here in the Northwest, but we've run out of capacity here with hydro, so we're moving to gas as well. So if gas prices spike, it makes the price of renewables more expensive. Okay, everybody loses. Now this is a slide now of gas in the United States, and as you can see, we have great reserves. So we hope that the price will stay stable. Again, the price has dropped recently as we've brought online new technology to access new gas deposits, and I hope that continues. I hope that we continue to have inexpensive natural gas, but there is a lot of data, and I have something here that's very recent from last month. This is the influence of methane leakage actually is detrimental to the environment as well. And I'm not trying to paint a picture that the gas is bad. What I'm trying to say is that I think the jury's still out on whether or not we'll have $4 gas in, let's just say, 2015. Mm-hmm. So this moves to our pilots. We're doing pilots here in the Northwest with 100 homes and several businesses where we're moving wind to water. And this is one of the promotional pieces that the PUD here that we're working with, one of the PUDs here that have put out and has been received favorably.
Good. Now we have a couple of things.
Sure. Now, what I wanted to show here is just simply with this PUD, we've got 100 homes, a couple of businesses, and we're storing power in hot water heaters based on a little device that we build. It's a gateway that will take a conventional water heater, receive a signal, and deliver power based on the control logic and the that we deliver from the cloud. We also have a couple storage units, as I mentioned. Actually, it's a 40 kilowatt hour, and it's been bumped up to a 10 kilowatt hour. The slide's a little dated. That are in businesses where we store off peak based on the renewables, and then we use that power during peak. We cycle those 2 times a day each, and we're showing increases in excess of 15% on energy efficiency, and increases in renewable power delivered to both homes and the businesses we're working with, increases of 20%. So the PUD, which is 32,000 customers, is looking at this as a way for them to shift out of peak and avoid BPA charges coming down the road in a couple months, as well as increasing their renewable delivered to their consumers, which has the response has been overwhelming to this program. We've had far more inquiries about signing up than we can support, but more importantly, they're looking at this as a way to aid the Bonneville Power Administration in the future to balance renewable energy and receive compensation for that. So let's see. Yeah, I think I just went over that slide. What I will say to that, what I don't see the.
You know what? I guess there's a problem with the presentation of slides that have tables in them. I'm sorry for this. I guess because that is a common denominator of the two that we couldn't see. I've never had this happen before. So do you want to? Why don't we just speak at a high level to electric vehicles and the value here?
Sure. So if you look at moving transportation from liquid fossil fuels to electricity, there's a couple of glaring questions that remain. The first one is that if you take EPRI data from 2008, they showed in no uncertain terms that there will be an increase in CO2 delivered from the vehicle, or from the vehicle moving 1 mile, if it were powered by 100% coal-fired electricity versus a roughly a 2006, 2007 gasoline hybrid. And the numbers are pretty interesting, because that EV on coal, so a conventional gas engine, and we can argue about the numbers, but these are the numbers that are presented in this study. Conventional gas engine generates about 448 grams per mile of CO2. An EV on coal, if you scale the data from this study, generates about 374 grams per mile of CO2. So that's very interesting. But here's the real interesting point: is a PV hybrid running on coal. Okay, PV hybrid generates 328 grams of CO2 per mile. Okay, so when you look at this at scale, and you think, well, if we're going to run our EV on coal, we might as well look at conventional gas hybrids. Conventional gas hybrid is 288 grams of CO2 per mile. Okay, so by 20%, a conventional gas hybrid creates less CO2 than that of an electric vehicle running on 100% coal-fired electricity. Now, there's assumptions taken into this, and we can attack this data, but this has been published and peer-reviewed. And what I would say as a scientist is that we're going to increase the efficiency of electric vehicles over the next few years, so the number is going to drop. But it is a fact that today that we could argue about running our fleet of vehicles on coal-fired electricity, of which coal generates about over 50% of electricity in this country, and the ramifications of that. The second thing I want to bring up has nothing to do with hard data, but it has everything to do with politics, and that is if we move to electric vehicle transportation, by and large, the early adopters are going to be in the major metropolitan areas. And if we look at the distribution of congressmen across the country, of which there's over 430, there's half of those that don't serve the major metropolitan areas. And how are they going to describe this passing of legislation to promote this to their constituents when, in fact, maybe all that their constituents will see is a higher price of electricity? Mm-hmm. And that's a reality that we have to address as a country. Now, what we're trying to do at Grid Mobility is take the same platform that we have in homes, same platform we have in businesses, and apply it to electric vehicles, essentially treating an electric vehicle and a fleet of electric vehicles as an asset that can be charged over a period of time, but better than just charging it indiscriminately over a period of time. Obviously, charging it when sending logic into the control infrastructure into the vehicle itself that states, well, let's maximize the renewables. Let's do our best to minimize charging during peak, which a lot of people are out there, but take the network that we've built here at Grid Mobility and apply it to the vehicle as well, that logic, which enables it to charge when there's the greatest amount of renewables delivered. So taking it as an example, you have your fleet of 100 postal trucks in your town of electric vehicles, and we're talking 2016 now, but they go and plug in the afternoon, and they need power by the time people come in the next morning and leave for their routes at 6 to 8 a.m. Now, you don't care that when it's charged over that 6 to 12-hour period, you just care that it's full in the morning. Okay, so what we're promoting here is if you have that kind of of input of end game, then what we can do is time when the power is being delivered, so that it coincides with the intermittent renewables that are delivered overnight on the grid.
Absolutely. And by the way, this gets, somebody asked a question about your thing with the water, and said, are we storing hot water, or he's not sure what we're talking about here. So the concept is simply that you can heat that water to a degree when you want to. To the degree you have flexibility on when you want to do it, this is a set of logic that says, okay, I want to draw that energy off the grid now, at time X as opposed to time Y, simply because it's cleaner at time X.
That's right. A water heater is a great example. Most water heaters in your home, in our homes, are 60 gallons. There are those homes that have 100, 200-gallon heaters, but most are 60 gallons. Most are insulated, and most have a temp delta T. So the low end is typically down 115 degrees Fahrenheit. The high end is 132 degrees Fahrenheit, somewhere in that neighborhood. And so that 17-degree Fahrenheit delta T will deliver you water to your house for showers, etc. But you don't really care that the power, because of the insulation, you don't really care that the water heater is heated up at time X, like Craig said, or time T, which may be 30 minutes later. Okay, all you care is that you have hot water when you turn on your faucet. So if you allow logic, just local logic on your water heater to talk to the grid and say, wait a minute, give me an hour plus or minus to heat it up, because I have insulation on it. I'm only going to drop 1 degree Fahrenheit per hour. Okay, so it's not as though I'm not going to have hot water, but give me the ability to heat up plus or minus an hour and time it with renewables delivered. Well, everybody wins there, right? You have the ability to use more renewable energy. You know that because we you can see it on a screen that we have, a UI. But more importantly, the utility can proactively balance the grid, if this was at scale, with water heaters in homes.
Yes, exactly. Now, skeptics are going to say probably the same thing I did when I first heard about this thing, and that is that if I right now knew that I could not be heating my water, I don't need to heat it right now, and now is a bad time to do it. And if I shift that to 45 minutes hence, because that's a particularly green time, if I'm the only person doing this thing, it actually, I think, I'm not 100% clear on this, but I think it makes essentially zero difference, because all I'm doing, I'm getting greener electrons, but somebody else is getting browner electrons. Now, so in other words, until there's a statistically valid sample of people doing this, and the power companies can say, you know what, we don't have to do this thing, and these peaks are moving. So now we can make commitments to buy wind energy where before we couldn't. In other words, that's the win on this thing, isn't it, Jim? In other
Absolutely.
Yeah.
And this is this is the big question. It's one thing to do this in 100 homes. It's a completely different set of variables when you do this in, let's just say, 100,000 homes, because the ramifications of that are today, the trigger which we have is just 2.5% capacity, could shift the peak, the utility peak, from time X to time Y.
Yes.
And if time Y they haven't forecasted for that, or don't have the generation, that's potential for brownout. But look at it this way: this is not going to go at scale overnight.
Right.
And what this is no different than the internet and coming on board and people having access freely to information. If you have access to the transparency of your grid and are able to make a decision on when to use power based on renewables, it's a forcing function. Okay, it's a forcing function to the utility, to the RTO and ISO, by saying, wait, we're seeing people really truly want to contribute to energy security in America by using less foreign oil, or
really want to contribute to using less CO2. And we can see it because we're watching them sign up for this program. We're watching the shifts in real time on a grid. We're going to have to deliver more renewables, folks. It's just that simple.
That's
now,
exactly
that's a very big, that's not going to happen overnight, and I don't want to, paint an illusion here, but that is, Craig, as you just articulated, the big picture.
Okay, well, very good. Why don't you say a couple words about the products, and then let's just end off for the day. I think this has been a fantastic session. Thanks very much for being here. You want to talk a little bit about your specific products?
Sure. I realize we've gone over time, and I appreciate those that are still with us. So we have several patents, U.S. patents, international patents, to collect and analyze and signal real-time electron sources on the grid and then connect those control devices. So we build a software-as-a-service platform. You would say it's in the flavor of demand response, but we've trademarked renewable demand response, and that delivers information to a whole host of assets, existing assets. It's open ADR compliant. It integrates into digital control systems, legacy control systems, because it's a signal with that's not unlike price. It just has different business logic, price being one of the variables in it. And then we have a power accounting platform on the back end that quantifies and validates energy use based on the generation source. Mm-hmm. So anyway, that's what we do. We see commercial, industrial, EV fleets, and as residential as our customers. We're working through partner channels in the energy services space, in the IT space, and in the EV space. So that's our product suite. Our value proposition, of course, is to save money, and we save money by. If you go to the next slide. If you have that, maybe not. There you go. We save money by shifting peak demand. We bring efficiency to the infrastructure management and also aid companies to meet their corporate sustainability goals. As we've talked about today, renewable integration and grid balancing to meet RPS is one of our value propositions. It's the one that seems to resonate the most with our utility customers. Because they have looming challenges in front of them. And finally, we offer an alternative to renewable energy credits. This is pretty standard, but we have the ability to track, quantify, and validate renewable energy use. And so the corporate clients that we've talked to, the two that we're working with at scale now, see this as an ability to save green dollars.
Fantastic. Well, do me a favor. Let's close. By the way, one of our listeners wants to be in touch with you. He does residential energy monitoring, etc. And I will connect the two of you. Is there anything else I can do in terms of a kind of business push here? Where are you? Did you mention that you're looking for investors, or where are you in terms of corporate development?
So thanks for bringing that up. We have been self-funded thus far. We've been in business a little over 2 years, and right now the founders do not take a salary. We are in the semifinalists in the National Clean Tech Open because we're now ready to go out and speak to investors. We're at a stage now where we have traction in all of the market verticals that we want to pinpoint, but we need to scale. So to scale, we need capital, and so we are out speaking to investors and would welcome inquiries from the group that joined us today, should there be an interest.
Yes, and if there is, just please let me know, and I'll connect you just as I'm connecting Jim with his fellow in residential energy monitoring. Jim, thanks a lot, my friend. This has been fun, and let's talk again soon, okay?
Okay. Thanks, everybody, for joining us today.
Okay. Thank you, everyone. Bye now.